In this last video, we're going to continue with raw scores and probability, but we're going to be looking at it in a very different way. So let's take a look. So the process that we've been using can be reversed. We can use a z-score and a proportion to find an x-score. You might be thinking, why would we want to do this? Why would we ever not have a score? Well, sometimes we don't know the score. Sometimes we know the z-score, we know the proportion, but we don't know the actual raw score. Let's say that perhaps you're interested in going to graduate school someday, and there's an exam called the GRE, and that is an exam that you need to take for many graduate programs, and schools will accept people who are in the top certain percentage. So let's say that the school that you're going to apply to only takes the top 15%. Well, if you know the mean and the standard deviation of the test in general, you can tell what score is needed to be in that top 15%. So what we would do is we take some very key information. You take your mean, your standard deviation, and then we would turn that top 15% into a probability or a proportion. We're looking for 0.15 in the tail, right? So what is a z-score that's associated with 0.15 in the tail? Let's take a look. So we have the table here, and we're going to look for 15% in the tail. We're looking for the top 15%, right? The closest thing we have to that in the column C, proportion in the tail, 0.1492, which is associated with a z-score of 1.04. So now we know the mean, the standard deviation, the probability, and we know the z-score is 1.04. And from all this information, we can figure out what raw score is needed at 1.04. So let's take a look and see how that works. I will say that when we're doing the next few problems, we're going to use two different ways of getting at x. One, we could use algebra, or two, we could use the formula that I introduced last week, the easy formula for finding a score when all you know is the z, the standard deviation, and the mean. We have all the needed information now to find the raw score that's associated with a z-score of 1.04. Our mean of 500, standard deviation of 100, and the z of 1.04. As a reminder, here's the z formula. I'm going to show you how to use algebra first to figure this out, and then I'm going to show you with the handy formula. So we know the z is 1.04, and we know that the z is equal to whatever score we have, which we don't know, minus the mean of 500 divided by the standard deviation of 100. Now I'm going to show you with a little algebra how to get x all by itself. The first thing I'm going to do is I'm going to get rid of this 100 in the denominator. To do that, I'm going to multiply each side by 100. So that gets rid of that, and 104 times, or 1.04 times 100 is 104. So now we have 104 equals x minus 500. I still need to get x by itself, so I'm going to add 500 to each side. So now I have a total of 604 is equal to x. So my x score is 604. The score that is needed to score in the top 15% is 604 or above. Let's use the formula to figure this out. As a reminder, the formula is the score is equal to the z times the standard deviation plus the mean. So we can do that very easily. X equals the z of 1.04 times the standard deviation of 100 plus the mean of 500. So basically, x is equal to 104 plus 500. X is equal to 604. All right. Let's try some other learning checks. We have a normal distribution with a mean of 100 and a standard deviation of 20. What raw score is going to separate the top 40% from the bottom 60% of the distribution? Well, we know the mean, the standard deviation. We can figure out the z-score when we know the percents that we're interested in. So if we're looking for the top 40%, we're going to look for something close to 0.40 in the tail. And there it is, I found it. You know, it's interesting. This problem says the top 40% from the bottom 60%. You could also find the bottom 60% in the proportion in the body. But that's neither here nor there. The bottom line is our z is 0.25. And now that we know our z of 0.25, let's plug it into the formula to figure out what raw score we were interested in. The z-score associated with the top 40% was 0.25. We can plug all this in to figure out what x is at 0.25. So I'm going to start with 0.25 here for the z is equal to whatever score it is minus the mean of 100 divided by the standard deviation of 20. So what I'm going to do first is I'm going to try to get x by itself, obviously. I'm going to multiply each side by 20 to get rid of this 20 here. And if I multiply 0.25 by 20, that gives me 5. So 5 is now equal to x minus 100. Now I can just add 100 to both sides to isolate x. So x is equal to 105. In other words, the score that is at the boundary of the top 40% is 105. So let's try the easy formula with this. Once again, the easy formula is x is equal to z times the standard deviation plus the mean. So we don't know x yet, but we do know the z is 0.25. We know the the standard deviation is 20. And we know the mean is 100. We know that 0.25 times 20 was 5 plus 100. So x is equal to 105. Here's the next one. For a normal distribution with a mean of 100 and a standard deviation of 20, what is the minimum raw score needed to be in the top 5% of the distribution? All right, so how are we going to find the z-score for this first? We're going to look for 5% in the tail because it's the top 5%. Uh-oh, it's this one again where you have 0.0505 and 0.0495 equidistant between the two numbers to get to 0.05. If you will recall, though, we're going to choose the z of 1.65. Let's plug the z of 1.65 into our formula to figure out what score is required. This time we're looking for the top 5% of the distribution, and we found that to be a z-score of 1.65, but we don't know what raw score that would be, so let's plug it all in. The z is 1.65. It's equal to whatever score we have minus the mean of 100 divided by 20. All right. So what I'm going to do is I'm going to multiply each side by 20 in order to get rid of this down here. So 1.65 times 20 equals 33 is equal to x minus 100. All right. And so I'm going to add 100 to both sides. And that gives me 133 equals x, or x equals 133. Shall we check that with the handy formula? Let's do it. So here we go with the formula. We don't know x, but we know z. So we know that x is equal to the z of 1.65 times the standard deviation of 20 plus the mean of 100. So we can just do the math. 1.65 times 20 is 33 plus 100 here. So x is equal to 133. It worked just the same with the handy formula. Okay. For this last one, we're looking at the raw scores that would form the boundary of the middle 60% of the distribution. And what you will recall is that our unit normal table only goes up to 50%. It only represents 50% of the distribution. And so what we're going to have to do is we're going to have to take that 60% and divide it into two pieces, between the mean and 30% on one side and between the mean and 30% on the other side. So we can do this. So what we're going to do is we're going to look for which column? We're going to look for the proportion between the mean and z, something close to 0.30. We come up with 0.2995. And that equates to a z-score of 0.84. So what we're going to do now is we're going to plug this 0.84 into the formula in a couple of different ways. For this last one, we're just going to use the handy formula because we're going to be doing a couple of different things, and I want to keep it as simple as possible. You could still use algebra with this, but let's just make it simple. So we have a z of 0.84, but we also have a z of negative 0.84. Remember, we're looking for the scores that encompass the middle 60%. So one z-score is below the mean and one z-score is above the mean. So we need to figure two different scores that are associated with each of these z-scores. So the first one, let's do the positive one first. So we have x is equal to our z of 0.84 times our standard deviation of 20 plus our mean of 100. So that means x is equal to 16.8 plus 100. 0.84 times 20 is 16.8. So x is equal to 116.8. So that's the raw score that's associated with a z of 0.84. So I'm going to put that up here. 0.84 z is equal to 116.8. Now let's look at the negative z-score. Let's plug it into the formula. But what we can't forget to do is make this z a negative 0.84. Very important. Times our standard deviation of 20 plus our mean of 100. So x is equal to negative 0.84 times 20, which now becomes a negative 16.8 plus 100. So now basically we're taking a negative and adding it to a positive, which means that x is going to be equal to 100 minus 16.8, yes? Which gives us 83.2. So just to reiterate what this means, so our negative 0.84z is going to be equal to 83.2. That means if you're looking at the middle 60% of the scores, the lower boundary is 83.2 and the higher boundary is 116.8. That means that 60% of the scores are somewhere between 83.2 and 116.8. How about that? That's a wrap for lesson 6. Remember that probability is the cornerstone of inferential statistics. It helps us to form a link between samples and the populations from which they came. Also, remember that we use proportions of a normal distribution and z-scores to determine the probability of events. An event being something like, how likely is it to find a score of 110 or above, for example. So this is lesson 6 in a nutshell. And when we look ahead to lesson 7, we're going to talk more about this probability and how it forms this direct link between samples and populations. And this link is what we need for inferential statistics. We're almost to the point of being able to do some statistical tests using inferential statistics. So I hope that you bring all of your questions to the Hallway Conversations Forum. This is important information to know now, and I hope you have a great week.